Hello and welcome back. In this video, we'll be working through an example where we'll find the tangential and normal components of the acceleration of a circular trajectory, given by the vector-valued function shown here. Remember, in the last video, we worked through the derivation for these components of the acceleration. We found that the tangential acceleration is given by the second derivative of the arc length function with respect to t. Remember, this is the same as the derivative of the speed function with respect to t, because ds dt, the first derivative of the arc length, is speed. And the normal acceleration is given by curvature multiplied by speed squared. So let's see what these components are for a circular trajectory. Again, it's a good idea to make some conjectures before we actually compute this. For instance, we can ask ourselves, does this have a normal component to acceleration? Is it constant or variable? Does it have a tangential component of its acceleration? Is that constant or variable? Things like this are important. We're seeing this circular trajectory in a little bit more general of a form than we're used to, right? Usually we just have like r cosine t and r sine t. Remember, r is the radius of the circle. With this omega added here, we've looked at an example where omega was 2 and we compared that to when omega was 1. This omega here, this is our angular velocity. Angular velocity. Not super important to know this, but if you've seen this form before, you might recognize that that's angular velocity. So that just affects the speed at which we go around the circle. And it is given here as a constant. Let's go ahead and start computing the components of the acceleration here. So for both of these, let me just remind myself what these are. So tangential. And how I remember this tangential component of the acceleration is, right, so this is along the trajectory of the object. This is like braking or accelerating, if you're in a car hitting the accelerator or the brake. And so I know that this has something to do with speed. In particular, it's the second derivative of the arc length function with respect to time, which is the derivative of the speed function with respect to time. And then the normal component is curvature times velocity squared, or rather speed squared. So for both of these, well, we're going to need curvature. One thing we can actually remember right off the bat is what the curvature is for a circular trajectory. Remember this omega, this is the speed at which we go around the curve. This isn't going to impact what the curvature is. Remember, curvature has to deal with just the shape of the trajectory and not how fast we move around it. And so we can remember, without having to compute curvature again for the circle, curvature for a circle is 1 over the radius. So 1 over big R here. So we're going to remember that so we don't have to compute curvature again. And now we're going to have to get a hold of speed. And for that, we'll need velocity. So let's go ahead and find v of t. So this is going to be, minus omega r sine omega t. And then finally, we'll have omega r cosine omega t. Don't forget your chain rule. So speed then, or we can think of this like ds dt if we want. Our speed then is the magnitude of this, so that's going to be square root of omega squared r sine squared of omega t plus omega squared r cosine squared of omega t. We have sine squared of something plus cosine squared of the same thing, so those combine to just be 1. And so we just have omega squared r. Oh, they should be r squared, right? And so we just get square root of omega squared r squared. Now omega, we're assuming, is positive. I'm going to go ahead and just say omega is positive here. And same thing with r. R is also positive. I'm going to go ahead and put those restrictions on it. That way I can say square root of omega squared r squared is just omega r. And so here's the speed of the object in terms of its angular velocity in the radius of the circle. Now, if you've taken some physics classes, some mechanics classes before, you should recognize this, right? Speed, linear speed, is omega, angular velocity, times the radius of the trajectory. Okay. So let's see. Let's refresh. What are we doing here? Let's go ahead and find acceleration, the tangential acceleration. So I already have my speed function. That's omega r. Notice that this is constant. So the second derivative of speed that's the derivative of just omega r, and this is constant with respect to t, so that's 0. Hence, this circular trajectory has no tangential acceleration. And that should make sense because we're not increasing our speed as we go around it. All we're doing is turning, right? We're not going faster and faster around the circle. We're keeping a constant angular velocity around the circle. So that's why we get 0 tangential acceleration. All of the acceleration should be normal to the trajectory. So again, we have speed, so that's omega r. So speed squared is omega squared r squared times k, which is 1 over r. So let's go ahead and find now normal acceleration. Now, by the way, since we could just find acceleration, we could take a derivative here. We could just find acceleration, and that should give us our normal component. Oh, wow. So I've made a little bit of mistake here, right? This acceleration tangential, this is not a vector. So I've made a mistake here with this. These are not vectors. Again, I don't like stopping and erasing all of that. It's good to know these are not vectors, right? These are, remember the whole idea is we break down acceleration into a scalar quantity times tangent vector. Oh, again, I've put an arrow over AT. Right, that wouldn't make sense. AT is a scalar quantity. It tells me how much acceleration tangential to the curve. And then we have a sub n, a scalar, times the principal unit normal vector. Right, so those are scalars. So pardon that mistake, but it's always good to point out those mistakes when we make them, and I like to try and describe why, how I made that mistake, why I made the mistake. So the normal acceleration is curvature, that's 1 over r, times speed squared, so that's omega squared r squared, and so it's omega squared r. And again, this may be familiar to you if you've taken a mechanics class before. You may have seen this centripetal acceleration given by this equation, and that's really what we're talking about here is sort of centripetal acceleration, normal acceleration. And there we have it. There is the components of the acceleration on the circular trajectory. So we can say acceleration, the whole vector of acceleration, it's 0 along the curve plus omega squared r along the principal unit normal vector. Pretty neat. In the next video, we'll take a look at a parabolic trajectory, and we'll break this down. And remember, the idea here is to think about a driver rounding a corner. And so we'll work that one out in the next video. I'll see you there.